Hello, Bacho, and a very warm welcome to the class. Today, we're diving into a really important topic from our second unit, electrostatic potential. Now, I know the name sounds a bit heavy, but trust me, it's the key to understanding all of electricity. And my promise to you is that by the end of this session, it will feel super simple, crystal clear, and you'll be perfectly ready for your exams.
So, instead of starting with some boring formula, let's begin with a curious question, something you might have seen in real life. Have you ever looked up and wondered about this? You see these birds just chilling on massive high-voltage wires, and nothing happens to them. How is that possible? Well, the secret answer lies in understanding today's topic, so let's pay very close attention. Okay, before we even touch the textbook definition, let's build a really strong foundation. We're going to use a simple picture in our minds to understand the main idea first. Right, just think about gravity for a second. We have hills and we have valleys, right? In the same way, you could imagine the space around electric charges as having its own, well, an electrical landscape. A landscape with electrical hills. So, imagine you have two positive charges. You know they repel, right? So trying to push them together is tough. It's just like pushing a heavy ball up a steep hill. All the effort, all the work you do against that repulsion gets stored up as potential energy. Now, here's the key part. The height of this electrical hill at any specific spot, that height is what we call electric potential. Simple. The top of the hill is high potential, and the bottom is low potential. So you might ask, sir, why do we need this idea of potential? Well, think about it. Calculating the force on every single charge again and again is very tedious. So physicists came up with a clever idea. They created a standardized map of the electric field. This map just tells you the height at every single point. That way, you know exactly how much energy it would take to put any charge there without having to do the force calculation every single time. It's much smarter. All right. Now that the picture of the electrical hill is clear in our minds, let's look at the formal textbook definition. This is very, very important, Bacho, because this is the exact language you must write in your exams to get full marks. Let's read it carefully together. It's the work done to bring a unit positive charge from infinity to that specific point. The most important words here are unit positive charge. That means we are measuring the work for a standard charge of +1. It's our reference point. Don't let the formal words scare you. In simple language, what does it mean? It's just the potential energy we talked about divided by the charge. That's it. We're just standardizing the energy. And this brings us to the main formula for today. Potential, which we write as V, is equal to the work done, W, divided by the charge, Q. The unit for this is joules per coulomb, which we call a volt. Okay, theory is one thing. Let's see how this actually works. We'll build up the concept logically and then solve a tiny numerical example. No complicated maths, I promise. You see how logical this is? Step 1, you have potential energy, U. But the issue is, its value changes depending on how big your test charge Q is. A bigger charge will store more energy at the same spot. To create our standardized map, we need to remove this dependency on Q. So what do? Step 3, we just divide the whole thing by Q. And what's left is potential, V. It's now a property of the location itself, not the charge we put there. Let's solve this quick problem together. This is a very typical kind of question you might get. So we did 100 joules of work to move a 5 coulomb charge to a spot called point P. The question is, what is the potential at that point P? So what do? Simple. We just use our formula. V equals W by Q. The work, W, is 100 joules. The charge, Q, is 5 coulombs. So 100 divided by 5 is 20. The potential at point P is 20 volts. It means point P has an electrical height of 20 volts. See how easy that was? Now for a very critical section. Everybody, full focus here. Let's talk about the common mistakes, the silly errors that can silently kill your marks in the exam. This is, without a doubt, the #1 mistake students make. They mix up electric field and electric potential. Please, please remember, the electric field is a vector. It has a direction, an arrow, but potential is a scalar. It's just a number. It can be positive or negative, sure, but it does not point anywhere. Here's a trick to remember this forever. Think about temperature. If I say the temperature in this room is 25 degrees Celsius, does that temperature have a direction? Is it pointing up, down, left, or right?
No, of course not. It's just a value at a location. Potential is exactly the same. It's a value, not a direction.
Excellent work, everyone. We're almost done. Let's just quickly wrap up everything we've learned and see how this topic connects to the rest of your physics syllabus. So, what are the most crucial points to take away? First, potential is a property of a location, not a charge. Second, the formula is simple. V equals W divided by Q. Third, and this is super important, it is a scalar quantity, so you just add the numbers like regular math. And finally, if you ever get confused, just remember our electrical hill story. And why did we spend all this time on this one idea? Because the difference in potential between 2 points is what we call voltage. And voltage is the push or pressure that makes charges flow as current. So this concept is the absolute foundation for your entire next unit, current electricity. If you understand this properly, I guarantee that unit will become very, very easy for you. So we understand this electrical height, this electrical pressure, which leads to one final fascinating question. Is there a way we can store it? Can we bottle up this potential energy and save it for later use? Well, that question leads us perfectly into the very next topic of our unit, capacitance. See you in the next